Welcome back to my survival guide to mathematics. My name is Adam Jacobson, and today we will be discussing functions of one variable and the derivative. In economics, we very often use functions. A function could, for example, be a profit function for a firm, telling the firm, okay, given that you produce 10 units of output, this is the profit you will get. Or for a consumer, a utility function. And a utility function will tell the consumer, okay, given that you consume 10 units of production, this is the utility you will get. And in conjunction with this, we would also like to know how do these functions change when we change, for example, the level of output for the firm or the level of consumption for the consumer. And that is why we are interested in the derivative. That is, how much does the value of the function change when we increase the output, for example, for the firm, or the level of consumption for the consumer by 1 unit. So that is the topic for today. So, first of all, mathematically, what is a function? Well, a function, which is written like this, f of x, and this doesn't mean f times parentheses x, this is a function that is a function of the variable x. And so that is a rule that assigns a unique real number f of x to each real number x. Okay, so what does that really mean? Let me give you a few examples. Okay, consider this function. F of x is equal to 3 times x plus 2. So here you can see that, okay, this is a function, that is a rule that tells us a value of this function for any given value of x. And the rule is, okay, the value is 3 times x plus 2. This is the general function, right? But then what if we input specific values of x? For example, f of 1. That means if, well, x equal to 1, that means that, okay, we evaluate this function at x equal 1. So it's then going to be f of x is 3 times 1 plus 2, and that is 3 plus 2 equals 5. And let's say f of x equal to 2. Then what is then the value of this function? Well, it's going to be 3 times 2 plus 2 equals 8, and so on. So this is the function, that's a rule that assigns a real number, that's the f of x, to each value of x. So here when x takes the value 1, the value of the function we get is 5, and when x is 2, the value of the function is 8. Let's now look at one example from economics. So we call that an econ example. So let's consider a firm that's interested in its profits, as quite usual in this field. So we say that profits and we usually denote that by pi, not 3.14, etc. But usually we use this symbol to say, okay, profits, okay, that's pi. And that is equal to a function, and x, let's assume that is the output of this firm, how many things this firm produces and sells. And what is then profits? Well, for a firm that is active in a market that is has perfect competition, then the firm takes the price as a constant. So when we calculate profits, we want to first know, okay, what is the revenue? How much money does the firm get in? Well, that is going to be P, that's the price in the market when they sell 1 unit of good, times X, that is the number of goods they are selling. But then also there's a cost side to things, unfortunately, for the firm. And that is minus, and then we use some C here, that's a fixed number, a parameter, times X to the power of 2. This is just one example of one possible profit function. So here we have revenue, and this is cost. And revenue minus cost, that is profits. So, but looking at this from a mathematical point of view, we know that the X here, the X, that's the quantity produced, that is the exogenous variable. We say that, okay, we did just decide at the level of production 5, what is then the profit? So that's a number we take exogenously outside of the model. So we call the X the exogenous variable. And it pops up in 2 places. Okay, X, that's the exogenous variable. It comes outside of the model. Then pi here, that is a result, right? That's also a variable, but it is the endogenous variable, because this variable is decided by this rule, this function here. So it's a product of what we're doing here. So we call this the endogenous variable. So that is very important for you to know. What is an exogenous variable? Well, it is something that is decided outside of the model. The endogenous model is something that is decided by the model itself. And these variables are sometimes also called, the endogenous one is the dependent variable. And the exogenous one is then, as you might guess, the independent variable. Okay, so what is then P and C? Well, I sort of mentioned that. P here, that is something that we choose to put into the model, but it's fixed. And in a market that is characterized by perfect competition, then the firm takes price as given. So there's a fixed price for the firm. It doesn't matter how much they produce, the price is still going to be P. And we call this, in a function like this, a parameter. And the same goes for the C here. That's also a constant that is decided, before. And it is also called a parameter. Okay, so now we have the exogenous variable, parameters, and when we use these to calculate values, then we get the endogenous variable. Okay, so now we have put fancy mathematical names on all these things that we have in the function. But then, of course, the firm here, they would like to know, okay, how do these profits change when we change the level of production? That is rates of change. That's really important for economists and other people too, I guess. But what if the firm might ask the question, what if we raise production by 1 unit? Are the profits going to increase or decrease or stay constant? That is really important information. And to get rates of change, we are then going to need the derivative, and that is why we are going to continue with that. So what happens to profits when X increases? Well, starting, we can write this. So the change in the function here, that was profits. The big delta here means change, the actual change, divided by then the change in output. So you can see here, this is the change in output, the change in profits, and this is the change in output, right? So This is a rate of change. How much do profits change when we change the level of output? Okay, so that is what we are interested in. And this can be written in the following way. So then you would take what is then the level of output at evaluated x1 minus output evaluated x0. So this at, let's say this could be x at 2 and this could be x at 3. So how much will then profits change when we increase production from 2 to 3? And then we want to divide that by the actual change in output. So x1 minus x0. So if this was 3 and this was 2, there would be a 1 here, etc. Okay, so and so this could be for any change, a big change or a small change mathematically, right? This change here could be 2 units or 5 units or 6 units. But mathematically, when we want to calculate the derivative, we want to have this change here in the denominator as small as possible in order to get a point estimate. In this point exactly, the slope is going to be this much, because this is going to be a slope, right? And this can be expressed in the following way. So f of x0 plus h, so this is the increase in x, minus where we started, x0, that is the value of the function at x0, divided by h, which is the increase in x. And this ratio here is called the Newton quotient. And we will see in a short while how this can be used to calculate what is the derivative of a function. Thus, we are at this point. We want to calculate the derivative of a specific function. So, the derivative of f of x. And usually we write that in the following way: f prime evaluated x0. So this means the prime here means, okay, now we take the derivative of f of x. That is going to be the limit value, I will explain in a moment what that is, when h approaches 0. We want to make h, that is this change in x, as small as possible in order to get a really precise point estimate. So the limiting value of the function when h tends to 0. And that is then going to be the Newton quotient, of course, f x0 plus h minus f of x0 divided by h. And now you see why it says the limit value of this when h is tending towards 0, because we all know that h cannot be 0, can't be quite 0, because then this quotient is not defined, right? So maybe this is a bit abstract. This is basically saying, okay, how much does the function increase in value when we increase the variable in question with just a little bit, basically. So let's illustrate this. So we draw this diagram. So on the y-axis here we have f of x. And on the x-axis we have, not so surprisingly, x. Right, and then I just draw some sort of equation. Okay, this is a concave graph here, function, because we see the slope is very steep here and then it gets less and less and less and less steep. Okay, so this could be, for example, like a profit function. And then here, this is x0. And let's say this point here corresponds to x1. And then we can just by looking at what is then the value of the function f of x when we are evaluating it at the point x0. Well, it's going to be this f of x0. You go up here, you read off the graph, and you read off this axis here. This is the value of the function f of x when we input the value x0. And they take another bigger value of x1, and we do the same thing. And here we have f evaluated at x1. Right, and now we can see here that what is then, we were discussing the Newton quotient here. So this is the change in vertical, right? This is the value of the function at x0 plus h minus the value of the function at x0. So we can think of, if this is x0, then you see the difference between x0 and x1, that must be h. So this is h. If we move this far horizontally, how high up, much higher up will we then get? Well, that is this vertical distance here. This is the value of the function at x0. This is the value of the function at x0 plus h. So this distance here is then the value of the function f at x0 plus h minus f of evaluated at x0. So this is the change vertically, this is the change horizontally. And since we want to have the slope, that is, if my pen here is a tangent to this, you can see this is a tangent at x0. This is how much the function f of x slopes right here. And we can see that this slope here is another one than the slope at x1. It is not as steep here as it is here. And in order to get as a precise estimate as possible of what is the slope exactly here, well, then we must have a very small change in h, right? Because if we were to evaluate, okay, what is the slope of a line that goes between this point and that point, that would be not so steep, right? And the smaller we make h, then we can see that the tangent will be more and more and more steep, right? And we would approach the slope at this point. So let us then have a look at one example. Namely, let's assume that the functional form is this. F of x is equal to x squared. So what is then the derivative of this function? Well, it's going to be the following. Let's say it's f prime of x, that is the derivative of this function with respect to x. That is then equal to the limit value when h approaches 0. And then we write up the Newton quotient, which is f of x plus h minus f of x divided by h. We know this from before. But now we have an explicit functional form, x squared. So how would this then be? Well, still it's limit of this function when h approaches 0. And so we instead of x here, we can plug in the x squared function, or instead of x plus h. So it becomes the following. Namely, so first we have x plus h to the power of 2 minus x to the power of 2. So this is just the function is to the power of 2, right? And Here we have x plus h here, and here we just have x. And all this is divided by h. And now we can make use of the algebraic rules that we learned in a previous lecture. So this is equal to, in the limit when h approaches 0, so we can expand this, right? So it's going to be x squared plus 2xh plus h squared, then minus x squared divided by h. And this, in turn, is equal to, this was rule number 1 from the rules of algebra, if you remember, here. This is equal to the limit of the function when h tends towards 0. And here we have x squared, and here we have minus x squared, so they cancel out. Okay. So then we are left with 2xh plus h squared divided by h. And here we can see that the h here and this h here, h there, and h here, they cancel out. So this goes away, and the square term goes away here. So all this is equal to the limit when h goes towards 0, namely 2x plus h. But we see here that when h goes towards 0, so this goes away, right? So it's going to be 2x. Right, that's kind of neat, isn't it? So we started off with the function x to the power 2, then we found the derivative by applying the Newton quotient, and we plugged in the functional expression into that, and we saw that, okay, the derivative, the slope of this function evaluated at x, and then you can pick any x, is going to be 2x. So f of x and x, when f of x equals x squared, then we know that the function is going to look something like that. And we can see that the slope here is quite not so steep here and gets steeper and steeper and steeper. So the slope should increase, right, as we increase x. And we see here that the slope is twice times x. So the slope gets steeper and steeper and steeper, which makes sense. So it might sometimes be a good idea to double check, okay, this is the function, looks like this, and the derivative is twice the x that you are evaluating at. So for example, if this is 2, so then f of x is 4, and the slope f prime when x equals 2 is equal to 2 times 2 is 4 as well. And then you can go on and check and see that you get the right numbers. Now, that was one example. There is a more general rule, which you may have guessed by now, or perhaps you knew it, namely the power rule. And so that says the following. Let's say you have a function, f of x, and it is equal to some constant a times x to the power of n. And this is a version of x to the power 2, because then n is 2 and the a was 1. That was the example we looked at a few moments ago. But in this example, in this more general rule, we know that if this is the function, then this will then be the derivative with respect to x is the following. It's going to be a times the exponent n times x, and then you have the exponent minus 1. So this is a general formula. So let's apply that to the example we just performed. If f of x equals x squared, then f prime of x then should be, you see that the a here, that's a 1, so that's just 1, times the exponent n, which is 2, times x here, and then n minus 1. N was 2, so it's 2 minus 1. So we can skip this 1 here, right? Then we have 2, and we have x to the power of 1, which is x. And yes, the rule gives us the same answer as when we derived it using the Newton quotient. That is all for today. Thank you very much.